Good morning, good afternoon from Barcelona, and welcome to this new Rhino webinar. This is Pedro here, and I'll be presenting today with my colleagues at McNeil Europe, Carlos Perez and Guillermo Varela. We continue this series of videos where we discover new ways of using Rhino, by inviting and talking to experts. It's a pleasure for me to be here with Sergey Pigach. His work builds on his architectural training by bridging in some way the domains of technology and design, driving him to develop computational tools for architects, designers, and engineers. Since he joined Core Studio, he has worked on desktop and web-based projects, cloud compute solutions, and even new platforms based on machine learning. Today, we are going to learn how to make web requests directly from GH definition using his plugin Swiftlet. As a quick and fun example, we are going to fetch geospatial information from Google Maps API. So we are going to get real-time driving directions between 2 points inside a Rhino model. So I'll let Sergey start presenting. Carlos and me will be here in the chat collecting the questions you might have during the presentation for him. So Sergey, thanks again for being our guest today, and feel free to start whenever you want.
Sounds good. All right, let me share my screen. Great. Can you guys see my screen?
Sure.
All good? Perfect. Well, thank you so much. First of all, thank you so much for joining. And thank you very much to Carlos and Pedro and Guillermo and the entire McNeil Europe team. I'm very, very excited to be here. I'm an absolute Rhino fanboy, so it's very great to be here, and thanks for having me. So today I would like to talk to you about Swiftlet, which is a Grasshopper plugin that I've been working on for some time. And just to give you a little bit of a background about me, my name is Sergey Pigach. I'm an associate applications developer at Core Studio at Thornton Tomasetti. Thornton Tomasetti is a global engineering firm. We have offices all over the world. As per our elevator pitch, we can design anything from a shed to a skyscraper. And Core Studio is an R&D arm within Thornton Tomasetti. We're a relatively small group of roughly 20 developers. And our primary goal is to develop new tools and techniques, both within Grasshopper Rhino ecosystem, but also as standalone web-based and desktop applications, both for our internal engineers, but also for the AC community at large. So I have a background in architecture. I went to Pratt Institute in Brooklyn. I worked in the field for about a year and a half. And then after I joined Core, I was focusing on advanced modeling and parametric design. I worked quite a bit with Rhino and Grasshopper API development. At the moment, I'm a full stack .NET developer, and I'm leaning more and more towards machine learning and data science. And what I would like to talk to you about today is 3 things. So first of all, I would like to discuss web requests and what they are and how they work, how web requests can be used in Grasshopper and how they can help you augment your design workflow and what they can do for you as a designer. And also I would like to talk about Swiftlet and how Swiftlet can enable you to do all of those things easily from your Grasshopper definition. So first of all, why web requests? Like, why are we here and why do we care? The world, the internet runs the world, pretty much. And there's an immeasurable number of online services and databases and resources that are available through the web. And if you're able to tap into them, that opens up a lot of doors for you as a designer, an engineer, an architect. And some of the resources that you might find out there is access to real-time data, such as weather maps, public transit, live updates, social media activity, and so forth. You will be able to access massive public and private databases that would be impractical to host locally, or maybe you don't have the rights to host that information locally, but it is available through a database. You'd be able to access products and services that cannot be replicated locally. So Google Maps API that we'll take a look at later, IBM anomaly detection API, so on and so forth. Also, being able to make web requests makes it very convenient to even use things locally. So let's say you have a machine learning model that you trained and you want to run inference on that model and use it within your Grasshopper definition. Now, it is theoretically possible to bring that machine learning model and load it into IronPython inside of Rhino and try to call inference on it from like a Python component. But the setup is very, very difficult and very, very time consuming. And IronPython is notoriously difficult with third-party packages. So it's just a lot of unnecessary headache. What you could do as an alternative, you could spin up a very minimal Flask server or just any Python server, which we will also take a look at later on. And you'll just be able to make calls to that server from your Grasshopper definition. And this way, the server environment has to worry about all the dependencies and all the Python packages, but you don't have to try to bring this into Rhino in any way. Also, being able to make web requests opens up a lot of compute resources for you. So you're no longer limited by the processing capacity of the machine that you're working on. You can outsource jobs to a cloud compute cluster and let it spin up and run for a period of time and then shut down and give you the results. And even if you're looking for information that doesn't live in a database or doesn't live behind a certain API, you can still get to it by, good old web scraping. You can just crawl the web and look at pages and just parse the information that you're looking for out of HTML code of the websites that are out there. I want to very briefly cover web requests and how they work and how they're structured. I imagine that some of you on this call already know all of this. For some of you, it's going to be new information. But I think it would be a nice recap for everybody, but also it will let us understand a little bit better why Swiftlet is structured the way it is and what it is that it's trying to do in general. So the internet runs the world, and the internet is run by the HTTP protocol, or the hypertext transfer protocol. So HTTP is an application level protocol used to access the World Wide Web resources. The term hypertext refers to text containing links to other resources and text that the readers can easily interpret. And resources over HTTP are accessed via a URL, or Uniform Resource Locator. So all of you have seen a URL, right? This is the link that you enter into your browser. And this is the anatomy of this link, right? So we have our protocol, HTTP or HTTPS, which is the secure version that relies on encryption and certificates. We have our domain information. So we have subdomain, domain name, top-level domain, which are human readable components of being able that allow you to encode essentially an IP address in a human readable form. And then you would use like a DNS server, or rather your browser would use something like a DNS server to be able to convert this human readable domain into a physical IP address of a machine on the global network. Then you have the path, or the route, which is the location of the resource on the target host or on the target machine that you're trying to get to and query. And then you have the query string, or the query parameters, which are just additional parameters that let us specify some additional information about how we want to consume the information, or what kind of information we are looking for. And we are going to take a look at that later on as well. Now, for some of you, this is also another view of a URL that you've seen before. So instead of all of our domain information, we're looking directly at a raw host IP address and the port number. So this is a very direct way of accessing a specific machine and specific IP address over the network. And that's something you would do if you're trying to access another machine on your local network, or if you're running a server on your local machine and you want to call into it from a different application, you would use a local host IP address and some specified port. Port 80 is a default HTTP port. And once again, we're also going to take a look at it at a later time. And HTTP protocol assumes the existence of a client and a server, right? So we have an HTTP client, for instance, your web browser that sends a request to a web server, which is a server program that runs on some metal somewhere in the world. The server processes your HTTP request and fires back the HTTP response with the information that you requested. So in this case, it would be HTML code of a website that we're trying to reach. If you're trying to ping an API, that would be some sort of a JSON object or an XML, if you're into that kind of thing. So whatever information you requested, you're getting it back from the server. And let's take a look at the anatomy of the HTTP request. So this is literally what your browser sends to a website if you're using HTTP in clear text. So a good note here is that, yes, HTTP is entirely unencrypted. This is literally the package that would be sent by your browser to a website, which is also why it's a good idea not to browse HTTP websites on a free public Wi-Fi at a coffee shop, because anyone can intercept this package, and this is literally what they would see. But in terms of the anatomy of the HTTP request, so we have the request method. So in this case, it's a GET request. We'll talk about different methods as well. We have the path or the route, as we talked about. This is the actual resource on the target machine that we're getting. We have the version, and then we have HTTP headers. So HTTP headers is essentially a dictionary of keys and values that contain metadata that the server needs to properly process our request. So we can pass a content type header to specify what type of information we're looking for. So do we want text HTML if we're asking for a web page, or do we want application JSON, or are we looking for a CSV? So we can specify this and tell the server what it is that we need. Also, you can specify an authorization header so that the route that you're hitting knows that, oh yeah, this is an authorized user with an authorization token or some other means of authorization. So I should be able to reply to them and send them what they're asking for, or I can, instead tell them that, sorry, your token is invalid, and refuse a request. Or let's say we can pass a cookie. So, aside from tracking you all over the internet, cookies are actually very useful, because if you are shopping online, let's say, and you are going from one page to another page, you keep sending different requests to the same server, and everybody is doing the same thing. So a cookie allows the server to understand that, okay, these requests are coming from the same user. So when you jump from one page to another page in an online store, this is how you keep your items in your basket persistent across multiple pages. So in other words, headers just contain all this useful metadata for the server to better process our request. Now, an HTTP response looks very similar. So we have, again, the HTTP version. We have the response code. So 200 means OK, 404 not found, 403 forbidden, 500 internal server error. There's a bunch of HTTP codes. Once again, we have the response headers, which is the dictionary of metadata, but this time this is metadata sent by the server to the client, back to us, to help us interpret the response better. And again, we have content type and all of this good stuff. And then we have the response body. So the response body is the actual payload, so to speak, or the actual resource that we were asking for. So if you're sending a web request to a website to get a page, you'll have some HTML markup in here. If you're pinging an API, this would be some sort of a JSON object, and so on and so forth. It's important to point out that requests can have a body as well. So a get request doesn't, but a post request also allows you to attach a body, so you can actually submit an entity to the website. So a body is not just a response-specific entity. And let's briefly talk about different methods, right? So these are a handful of, I think a total of like 12 different HTTP methods. I only ever had to use these 5 in my entire career in software. So we have the GET request, which literally just tells us, hey, I want that thing over there, give me that thing, right? So we're fetching a resource. We have a POST request. So that allows us to submit an entity to a server, right? So let's say if I am creating a new account, right? And I'm entering my username and my bio and maybe my profile image or something of the kind, then I can submit all of this to the server as a POST request, and then this will be stored in some sort of a database. We have a PUT request, which essentially tells the server, okay, I'm giving you a resource or some sort of a payload, some sort of an object, and I want you to replace whatever it is at that link that I'm providing you. Whatever resource lives there, I want you to replace it entirely with this new thing I'm sending you. So if you ever talk to the S3 database, for example, so this is one of the things that you would have to do is to send a PUT request to S3. You also have a delete method, so that's pretty self-explanatory. It just deletes a resource from a particular URL. And you also have a patch request, which modifies a certain resource. So let's say if we have a database and we have some sort of a database object, we can send some fields and some new values to update them in the database. So this is just very generally kind of the 5 different HTTP request methods that you might encounter playing around with web requests. So just to recap, right, we have 3 main ways of submitting information to the server. We have query params, which become part of the actual URL. We have request headers, which is the key value dictionary that we mentioned before. And we have the request body, which is the payload that we are submitting to the server. And so how do we make web requests? So first of all, your good old web browser. That's what it does all day, submits web requests. You can also use tools such as curl, which are command line tools. They're available on Linux, and I'm pretty sure there's curl for Windows. You can use HTTP libraries in almost any modern programming language. Python, C#, obviously JavaScript, they all have very robust HTTP libraries. You can use graphical web debugging tools such as Postman, Insomnia, Fiddler. So these are little programs that just allow you to customize your web requests and see exactly what the server is sending back to you. Very useful for, developing APIs and the like. And then we have Swiftlet, which allows you to do all of those things in Grasshopper. So let's take a look at Swiftlet and what it does. So Swiftlet is a free open source Grasshopper plugin that allows users to construct and send web requests as well as parse JSON responses from API endpoints. And the way Swiftlet is structured, or the components that are structured, kind of follows the same pattern of constructing your web requests with headers, params, and the body, ways to construct the body through composing your JSON through multiple components that allow you to kind of put it together piece by piece, provide some authentication information, then make the actual request with one of those 5 methods that we talked about, and then parse the response that the server sends back to you. So this is the most basic example of Swiftlet sending back a response from just a simple GET request. So we have our URL to www.google.com, and we're sending it through a GET request. We're getting the results back, 200 status code, everything's okay, and we have the HTML markup fired back at us. And if you load this in your browser, you'll see the familiar Google landing page. Now, a more useful example would be hitting an API endpoint that actually sends you back not HTML, because you get the HTML text, you can then pull it apart and kind of parse it manually inside of Grasshopper, which is a little bit difficult to do. Swiftlet doesn't have any tools to parse HTML yet, but it does have tools to parse JSON objects. So here you have, an HTTP bin.org, which is kind of like a mock API that just lets you test different clients, which is very useful. So we just get some response from that test API back. Here's a real world example, right? So we're actually hitting a real public API endpoints to get current time in New York City. And we're looking at the JSON response that has all the information we could ever ask for about time in New York. Now we can also send post requests. So for instance, a different public time-related API, timeapi.io, we want to convert from one time zone to another. So we have a post body, which actually specifies our from time zone, our date time, and our to time zone. So we're converting from Amsterdam time to Los Angeles time. And we get, again, the response that we can parse through. We can also add query params. So for instance, this API route requires us to specify time zone as a query param. So you remember, those are the params that get added to the URL. We can easily do that. So we specify time zone as a key, specify the value as Europe Amsterdam, and we're getting current time in Amsterdam. We can also provide the exact same information inside of a header. Now, the previous API endpoint that we were looking at does not look for the information in the header. So if you were to pass time zone and the value to the header, in the header of the request, the API would return some sort of a bad request or some sort of a error message saying that, hey, I didn't find that time zone key that I was looking for. Because this is API specific, right? You have to read the documentation of the API you're trying to access to see what information you have to provide the server and where you have to put it. But yeah, we can pass it as a header as well. So in this case, we're pinging that testing API once again, and we're getting the request back. So if we revisit this diagram from earlier with the 3 different ways of passing web requests to the server, Swiftlet kind of covers all bases, right? So you have a component to add key value pairs to your query params. You have a component to add a header, and you have a component to compose a body payload that you can also send to the server. Now, Swiftlet has a number of components to help you with authentication. You can do all of this stuff just with the header and query components, but this just makes things a little bit easier for you. So we have the API key where you can specify the custom key name and the value, and it will automatically create a header param and a header output and a query param output, depending again on the API that you're trying to access. There's a basic auth component that takes your username and password and encodes them as a base 64 encoded string and adds them to the authorization header. This is a very outdated way of doing things. Some old API require you to do it this way, but this is a bad idea generally, because anyone can base 64 decode your credentials. And then you have the token auth, right? So you just pass a bearer token and it just creates a header for you. We have ways of parsing a JSON, right? So once we get that JSON string back from the server, we can actually use components to convert that string to a JSON token, and then we can pull out different keys and values. And once we get the values, we can cast them as string, number, and Boolean, because there's no really way to tell which data type lives at the particular key. So we just kind of cover all bases, and whichever one works for you and whichever one you need, that's the one you pick from that value. This is the genealogy of the J token and other more specific JSON types. So we have a JArray, JObject, and a JValue. And here they are, being parsed into those objects. An array of things, an object, or a specific value. And with Swiftlet, you can parse pretty complex and pretty nested JSON. So it kind of lets you drill down to very specific keys and really, regardless of how nested your JSON is, you'll always be able to get to that value that you need to get to just by chaining those components and by searching for those specific keys with the Swiftlet components. And it also goes the other way. So if you have to compose a JSON body to send to a server, you can also easily do it with Swiftlet. And again, it can be of any complexity and as nested as you want it to be. So let's take a look at some Grasshopper examples. So first of all, Swiftlet is on foot for Rhino, obviously. So it's available for Rhino 6 and Rhino 7. Some folks had some issues getting it on Rhino 6. The easiest thing to do is to download the examples file and just try to open it, and then Yak will give you a prompt that, hey, I can't find those packages. You click install, and it will install Swiftlet for you. Rhino 7 should just work out of the box. And it's also open source. So here we have a link to the GitHub repo. So here you have more examples that you can take a look at, and we're going to take a look at those examples today. And most of them are pretty well documented with README files and some instructions and so on and so forth. So this is the first example we will take a look at. So Swiftlet iris prediction. And this goes back to, again, this question of like, okay, so if I have a machine learning model that I want to run locally and I want to run inference on it and use it in Grasshopper, how do I set that up, right? So that's exactly demonstrating to you how to set this up on your local machine. So what we're going to do is we're going to open the repo, and there are two files that we care about. So we have server.py in Swiftlet iris prediction and train.py. So train.py is just your garden variety machine learning PyTorch deep learning network trying to predict an iris data set, right? Like this is as basic as you can get with machine learning. If you don't know what an iris data set is, that's kind of a legendary data set. It's a hello world data set in machine learning. It is as old as the moon. I think originally it was published in 1936 or something. So this data set is composed of 150 different instances of the iris flower. And there are 4 different measurements of different anatomical parts of that flower that let you predict one of the 3 classes. So which type of iris flower is that? So here we can see the data set itself. So yeah, we have the sepal length, sepal width, petal length, petal width, and then three types: iris setosa, iris versicolor, and Iris virginica, and I'm sure I slaughtered all three of those names. But anyway, so this is what we're trying to predict. Now, I'm not going to go through the code. This is, pretty basic in terms of putting together a machine learning model. We're scaling some values, defining the network, running the training, and so on and so forth. The two lines of code that we care about here are these two. So this line of code serializes our model, and this line of code saves it to disk. So that's all we care about. So what I'm going to do is I'm going to run this. So I'm using Anaconda. So I'm going to say conda activate Swiftlet. So Anaconda is a very nice way to compartmentalize different environments, virtual environments on your machine. And each of those environments can have a different Python version with its own set of packages. If you've ever tried to host multiple Python interpreters on the same machine without using Swiftlet, you know the pain. Without using Conda, you know the pain. So Anaconda just helps you manage your environments better. And I'm going to cd, and I'm going to copy path to this directory, and I'm going to change my directory into it. I prepared a little requirements.txt file. So in order to install all of the packages, you need to use this. You can just say pip install or requirements.txt. Now, obviously, I already have all of them installed, but for you, it will just grab all the correct versions of all the packages used in this example. So that's just kind of a nice little aid. And so what we can do now is we can say Python train.py. And it's a tiny data set, so it will take a few seconds. Okay, great. So we have 93% accuracy, pretty good. And then we have this model.pt file that just appeared in our directory. So that's pretty cool. We just serialized that trained model to disk. So now what we have is the server.py, which is the actual Flask server. And I'm going to talk about this in slightly greater detail. So Flask is a very, very popular server framework for Python. So we're importing all of the things that we need here. We're creating the Flask app. We are loading the PyTorch model that we save to disk. Then we specify the device. This is like a PyTorch specific thing, just to tell it to use the CPU and not the GPU. This is a little bit of a hack here. So deep models usually, they don't give you like a verbal answer, right? Like it won't give you a string as a response saying, oh, this is Iris setosa. Instead, you will have a number of nodes in your output layer, and each of those nodes corresponds to a specific class. So in that network, we have 3 output nodes. The first one for Iris setosa, for Iris versicolor, and Iris virginica, right? And then it will basically give you a probability for each of those, like what it thinks is the most probable one of the 3. And the way to convert this to the actual string is to just pick the index that has the highest probability out of 3, and then use that index to pull out of a list of actual classes that is ordered in the same way, right? There are better ways to do this. Some libraries allow you to actually pull out the classes from the actual trained model. I think XGBoost lets you do that. But anyway, so this is just a little hack. And then we have a method, a predict method, which actually does the prediction. And it has this decorator that basically just tells Flask that, hey, this is a route. So when you get a request asking for this predict iris route, request of type post, I want you to run this method and fire back the results of this method. So you remember in the URL, like that route that we're trying to access, that resource on the target machine, this is us creating this resource as a method that will return a response. So anyway, so we're getting the JSON from the request. This is just, moving the data around to make it the correct shape. Then we run the inference on the model. Then we, convert the inference results from the model, which are the probabilities, to the actual classes that we want. And we put together a response object and fire back that response object. In 60 lines of code, we wrote a web server, right? So I'm going to launch the server, and it will run on port 8000, which we specified here. So I'm going to go back to Conda and say Python server.py. And so it will take it a second to spin up. It tells us not to use this in a production environment, which is fair enough, because Flask is a single-threaded server. So you need some sort of a gateway framework like Gunicorn, which is also very easy to set up if you actually want to use it in production, because it will spin up multiple workers and kind of handle requests asynchronously. But this is good enough for just our test. And so we have the server running. It's running on localhost. So 127.0.0.1 is my local host IP address, so my local machine. And I'm going to go ahead and first ping it from Postman. So Postman is, as you remember, is one of those graphical interfaces that helps you make web requests. And so we're pinging HTTP localhost at port 8000 predict iris. I'm going to ping that. Sometimes the server locks up. I'm just going to hit enter. Again, this is why you need a gateway server to use it in production. So here we have a request 200 on the server, and we have our results with 2 iris types that we got back. Great, that's just what we need. So now we can do this from Rhino. So in that directory, there's the iris simple Grasshopper file. So we're not doing anything extraordinary here. This is basically the iris data set. Again, it's pretty small. There's only 150 values in there. Some of you may be wondering, it's like, well, why are we testing the machine learning model on the training data? Aren't you supposed to do that? Well, we're not really testing the model. We don't care about the model accuracy. We just want to be able to create realistic examples to run the inference, right? So you wouldn't be passing your actual data set here. You would just be passing, the inputs for the actual inference values that, or inference scenarios that you're interested in. So, okay, so we have our keys, which are these keys in our input schema, right? And we have these values. We create a bunch of JSON objects. So we have 150 objects coming out, one for each flower. Then we pass all of them to create a JSON array component. So it takes a list of objects and it spits out one JSON array with 150 objects inside of them. Then we stringify the JArray. Now, if you're running Swiftlet 013, you have to do this. So you have to turn this into a string before creating a request body. If you don't do this, it won't throw an error, but it will just, it won't actually create a JSON. It will just send a name of the object in the post request. So I fixed that in the version that's out now, which is 01.4. So you can actually directly go from a JToken to request body and it will serialize correctly. So in any case, so we can create the body and we're sending a post request and we got the results back. So we can look in our server. We have a second request with the code 200 saying that everything's good. And we have all of our flowers predicted properly, well, with 93% accuracy. So yeah, so that's pretty great. We just made a call from Grasshopper to our local server. Now, what if I actually want to use it, with some 3D geometry, let's say. So there's another file called Grasshopper Iris 3D, and this is basically, I mean, this is silly, but it just has a bunch of flowers modeled in Grasshopper, and each of those is modeled after the parameters in that original Iris dataset, so following those dimensions. So what can we do with this? So let's hide this preview, and let's once again send that request. We got our response back, and now we have all those flowers colored based on their flower type. And you can see visually that like the purple irises look very different from the blue irises that look distinctly different from the green irises, which means that this is working properly. If you're wondering if there's a more useful example of using this in production, which I imagine you don't sit around all day just coloring flowers in Grasshopper, then that's a fair question. So let me show you this demo, which we submitted to the North American Steel Conference this spring. So this is Swarm, which is just our web platform for running Grasshopper definitions in the cloud. So yes, it's in the browser. Yes, it's a web UI, but it's running Grasshopper in the background. And we created this machine learning model that lets you do steel connection design. So based on your big dimensions and kind of your loading conditions, you can actually calculate the number of bolts, the length of your shear plates, different kind of attributes about those connections. And now we're just showing how to color by all of that information. And yeah, calculate the weight of bolts and all this good stuff. And this is the Grasshopper definition that has Swiftlet components in it that is pinging the server running that machine learning model, doing the inference and bringing those results in Grasshopper and rendering the results. So this is all well and good. So what about the geospatial data that we talked about? So let's take a look at another example in the repo, which is this Swiftlet Google Maps API. So it requires you to get a couple of keys. So one from the Transitland API and Google Maps API. Transitland has a free tier. Google Maps API requires some setup. There are instructions here. I'm not going to go through all of them. It's all documented. Google Maps API is a paid service, but they give you a $200 credit each month. So chances are you're never going to have to pay for it. But you know, if you do have to pay for it, it's relatively inexpensive. So anyway, so let's take it for a spin. So I'm going to go to Swiftlet Google Maps API, and some of you may recognize the familiar boundaries of the 5 New York City boroughs. And I'm going to have to give a couple bits of information to the script. So first of all, I'm going to give it my Transitland API key. And here are my API keys right here. So I'm going to copy those and plop them in here. Here we go. And so, okay, so first of all, Transitland API. So this is going to take a little bit, like 10, 15, 20 seconds, because we're actually sending a request that will fire back a large amount of information. So yeah, exactly. So this is a lot of stuff. So what is this? This is a map of every bus route served by the MTA, the Metropolitan Transit Authority of New York City, in New York. And this is what the Transitland API does, right? So it collects information about all transit networks around the world. So let's take a look at this, right? So we have our API token, right? That we are using one of our auth components to pass as an API key to our GET request. And then we have a number of query params that specify what it is that we're looking for. So first of all, we're looking for a vehicle type. we can switch to Metro. And now you're looking at the New York City Metro. That's pretty great. Let's switch back to bus though, because it kind of gives us almost like a map of New York, because almost all streets are served by a bus. So we'll go back to that. Then we have the operator. So in this case, it's MTA New York City. They have operators all around the world. And also we have the number of results per page. When you're getting large amounts of information, usually the API will let you split it into pages and specify how many items per page you want to get back. And in this case, we're just saying like, hey, just give us everything at once. Sometimes it's not possible because there's just too much data to fit into an HTTP request, because those do have a limit. But yeah, you'll just have to like chunk it up and call several times. So anyway, so then we're just parsing the output, we're pulling out the geometry and the coordinates, and we're constructing Rhino points from the response that came back, constructing the polylines, and then coloring them based on the route color. So this is the actual color used by the MTA to specify that route color. And we're rendering them in Rhino. Now let's do something even more fun. So we have a Google Maps API key here. So I'm going to plug it in. And at first, nothing is going to happen. But I'm going to do two more things. So I'm going to create 2 points. One in Manhattan, one in Brooklyn. Brooklyn is going to be my origin. Let's say I want to go to Manhattan. And immediately you have this blue line appearing here. And this blue line is the Google Maps driving navigations for New York City in this case. And so how are we doing this? So again, we have our API key, right? We're passing this API key through the auth component. And then we are converting the coordinates of these points from Rhino coordinates to GPS coordinates. And then, so this is our origin and destination. And then we have a setting for the mode of transportation. So do I want to drive? Do I want to walk? Do I want to ride a bicycle? Do I want to use public transit? So we can do all those things. Now, if you need to do something like this in Rhino, I mean, I suppose you could do some sort of I don't know, like a shortest walk algorithm, like an A* algorithm. But again, then like your map of New York has to be a very clean graph. Also, it won't respect the fact that in a city like New York, most streets are one-way streets, so it won't know the direction that it's going to go to. So you could, in theory, reproduce this manually in Rhino, but it's really, really, really difficult to do. And there's no point, because all of those resources that work much better than whatever, you know, a single developer can put together kind of on their lap over the course of a month can do, they exist out there, right? And it's just a matter of calling into those APIs and taking advantage of those resources. So yeah, is there any practical utility to having Google Maps navigation in Rhino? Probably zero, but that just shows you once again that you can talk to all of those services and talk to all of those resources and take advantage of them in your design process. So this is really all I have for you today. I encourage you to come check out Swiftlet. It's up there. I will try to update it pretty frequently. Also check out the Grasshopper repo, the GitHub repo. It's open source. You can fork it, star it, whatever you want to do with it. Also, if you have any issues, please tell me about them. Just create an issue or send me an email. My email is also on Food for Rhino. So yeah, I'm very excited to see what you guys are going to do with this. And thanks again for joining.
Thank you very much, Sergey, for the presentation. It was, well, really amazing. I'm sure the attendants have enjoyed the presentation as much as we have. Well, if everyone wants to paste the questions in the chat for Sergey, don't hesitate to do it. In the meantime, Sergey, I don't know if my question goes first, for example. So how can you connect to private APIs to make, I don't know, put or path requests? Just by setting the authorization components into the header, or?
Exactly. So we kind of did that, right? So the Transitland and the Google API, well, the Transitland has a free tier, but it also has a paid tier. And I guess what distinguishes like public from private APIs is that it's not whether or not you pay for them, it's whether or not you need an authentication or authorization token to access them. So both of those needed a token, which is why we had to provide them through the auth components. And yeah, it's just a matter of like, do you have a token or some other ways of authenticating to that resource? And then Swiftlet has components to facilitate that.
Yeah. Okay, Pablo Arango has a question as well. He said that have you worked? I see a lot of opportunities to use Swiftlet with Hops. So have you worked with both of them in some workflows?
So not with, so absolutely, yes. The experiment that we showed, that I showed that we did with the Steel Connection Design app, that wasn't using hops, that was using kind of our proprietary Rhino compute clone, let's say.
Yeah.
But yeah, absolutely. You can have some sort of a server on your local network that has all of those Grasshopper definitions that use Swiftlet to call into web APIs. And you can use hops to access those definitions for sure, or some local definitions on your machine. So yeah, totally.
Okay, another question from Svetan. Is there auto refresh in Swiftlet to monitor any changes on the web page, on the database?
Are there any, sorry, what?
Auto refresh tool.
Oh, auto refresh.
Yeah.
So currently, no. I mean, I suppose you could do something like, the Grasshopper timer component, just to continuously ping an endpoint. Just be careful with, how frequently you do that. One of the things, I'm going to be very careful making promises on this call because, this is something I do in my spare time. So we'll see when it actually happens. But I had an idea that I wanted to play around with of introducing sockets to Swiftlet. And sockets essentially let you join a room, and then whenever a message comes in, it fires an event and does certain things. So that could be pretty cool for certain feeds or real-time data.
Okay. Well, I see a lot of messages about, well, congratulations you for the presentation. And thank you for translating this code about making web APIs into Grasshopper components. I'm sure that a lot of people are going to use them so many times. Yeah, how can I know which web sources can be used for Swiftlet? It's a question from Weigu.
Which resources?
Yeah, how can I know which web sources can be used? So
in general, I mean, anything you have access to, you should be able to use with Swiftlet, right? So it's just an HTTP client. So whatever you can get to with your browser or whatever you can get to with, like a mobile application on your phone, it's a question of whether or not you have authorization credentials, right? Do you have the token to call into the route? And you might have to find the documentation for the web resource that you're trying to call into, right? So a lot of the APIs will have docs that you can look through, and see like what query params are available, what headers you need to have, and so on and so forth. So it will require a little bit of research on a case-by-case basis.
Okay. Any questions in chat? No? Well, I think, Sergey, that we can finish here the webinar. Well, last question. Let's go. Keshava Narayan. Hi. There are like 15 maps APIs in Google website. So should I apply for each of them?
No. So yeah, there are instructions on in the README on Swiftlet. Google Cloud Platform is basically the same thing as like AWS, but by Google, obviously. So there's a ton of different resources, and you kind of have to enable each individual API that you need. So no, I think the only API you need here is I think it's called the location API or something. I'll double check, but yeah, you just turn on the things that you need to for this. Yeah.
Okay, Sergey, again, thank you very much for your time.
Thank you for having me.
We will wait for new features in the Swiftlet plugin. Let's see how the people is going to use your plugin. Okay.
Sounds good. Thank you.